In this vector, we're going to try to talk about forces here. So the question that we have is, let's find the angle between force 1, which is 3,000 pounds, and force 2, which is 1,000 pounds, if we know that the magnitude of the resultant, and the resultant is what we get when we add two vectors, is given by 3,750 pounds. So forces, remember, are going to be vectors. So if we like, we could put the little vector symbol above them. We're looking for the angle in between those two vectors, which I'm going to call theta. We are free to put these vectors anywhere we like. So to make our life easier, I'm going to put F1, that first force vector there, I'm just going to put it right on the x-axis. So remember the magnitude, which is the 3,000 pounds. Pounds are a unit of force. That's going to be its length. So I'm going to draw F2, and I don't really know exactly where it is, but I'm going to just kind of approximate it kind of over here, and I'm going to try to draw it so that it's about 1/3 the length of F1, and that's just a guesstimate because 1,000 is 1/3 of the 3,000. Now our idea is, if we imagine this parallelogram formed by those two vectors, then our resultant, remember, is going to be the sum of those two vectors is going to be that diagonal right there. That is our resultant vector. So to work this out, and we're trying to find theta, so our goal is to find this theta, the angle formed by the force 1 vector and the force 2 vector. So let's look at if we can resolve our forces into their components. Because we placed force 1 on the x-axis, all of its force is going along the x-axis. That's going to the right, so its components are going to be 3,000 in the x direction and 0 in the y direction. Now, force 2, its components are going to be, now remember this angle theta is in between there, so it's going to be its magnitude, which is 1,000, times the cosine of that angle between the x-axis and force 2. And the y component, the vertical component, is going to be the magnitude 1,000 times the sine of that angle. So what we know is that when we add F1 to F2, we're going to get that resultant. And so what we get for the resultant is going to be what we get by adding those components together. So we're going to get the 3,000 from F1 in the horizontal plus the 1,000 cosine of theta. That's going to be the horizontal component of our resultant vector. And then we'll get 1 plus the 1,000 sine of theta. So that's our resultant vector. And remember, our goal is we're trying to figure out what is that theta. Well, we know that the magnitude of that resultant vector is 3,750 pounds. And we know that the magnitude of a vector is that Pythagorean theorem. It's the length of that vector. So we are going to take the x component. Now these numbers are going to get messy. 3,000 plus 1,000 cosine of theta. We're going to square that. And we're going to add that to the 1,000 sine of theta and square that. And that we know is equal to the 3,750. Okay, well, let's see if we can square both sides and get rid of that radical. So I'm just going to leave it for a moment as 3,750 squared. We're going to square the radical, which will remove the radical. And now I'm going to square this because that's a binomial squared, which I know is going to be the first one squared, 3,000 squared, plus twice the product. So that's going to be let me go ahead and do that. 3,000 squared, 3 times 3 is 9, and then we're going to get 6 zeros, so that's going to be 9 million. Loving these numbers. Plus twice the product. 3,000 times 1,000 is going to be 3 with 6 zeros. Twice that is going to be 6 with 6 zeros. That's 6 million, and that's going to be a cosine theta. And then plus the second term squared, so that's going to be the 1,000 squared, which is going to give us a million cosine squared theta. Okay, this is turning out to be pretty fun. We're squaring the 1,000 sine theta. The 1,000 squared is another 1 million sine squared theta. Okay, now we're looking at that and seeing that we can combine a little bit here. Well, we can do some clever factoring. So I'm going to leave these first two as they are for a moment, but on these second two, let's see, on these right here, we can factor out that 1 million, and that will leave us with our favorite trig identity, cosine squared plus sine squared theta, which we know is 1. So all of that cosine squared plus sine squared is going to be just 1, times a million is a million, added to this 9 million is going to make 10 million. And that's plus 6 million cosine of theta, and that's equal to our 3,750 squared. 3,750 squared. So solving this for theta, we're going to take our 37, this is all going to go on our calculator here shortly, 3750 squared. We're going to subtract off the 10 million. That's going to get us to 6 million cosine theta. We will divide by the 6 million. And so we'll get 3750 squared minus 10 million, all divided by 6 million. Good thing we got the calculator. And then we are going to take the inverse cosine of that. If I can get my pen, I want to change color, but it's not cooperating. Here we go. So I'm going to take the inverse cosine of that, and I believe when you do that, you are going to get 47.4 degrees. And that's our answer. Okay, well, that was a good warm-up problem. Let's talk about something that's really tough. So I'm going to need a new screen here. I'm going to pause it for a moment here because I'm going to have to do some drawing, and then I'll come back once I have the problem all written down. So here we have a diagram. This is actually out of the Larson worksheet, page 419, number 78, if you want to see the whole problem written out. But here you can see my exceptional artistic skills. I've drawn 2 cranes. Those cranes have cables running from them that are supporting this massive weight of 20,240 pounds. So what we are trying to do is find the tension in each of the cables of the crane. So this is really a force question. So when it's asking for tension, that's actually asking for the force. So if you imagine, here's the point where that weight and the 2 cables come together. So there is a force vector coming out this way to try to suspend that weight, and I'm going to call that vector V1. And there's also a force coming along this cable coming out this way, and I'm going to call that vector V2. And then we also have this weight, and so that's a force vector also that's going straight down, and that's the 20,240 pounds. Now, the these are lengths of cables, so don't be misled that even though I've drawn those as, the blue and green and yellow vectors, their length there is not really equal to their magnitude. It's a different non-visible idea there, the magnitude of those vectors. Now I'm going to say that vector 1 is going to have components x1 and y1 in the x1 in the horizontal direction and y1 in the vertical direction. And because I'm going to be referring to this a lot, I'm going to rename this magnitude of vector 1. I'm going to call it M1 just because it's easier than writing that symbol for magnitude all the time. Similarly, I'm going to say vector V2 is going to have horizontal and vertical components x2 and y2, and I'm also going to call the magnitude of vector V2 capital M sub 2. Now, there is a law of physics that applies here, and that is that at rest, so what we have let me just say it, at rest, the sum of the horizontal and vertical components are going to be 0. The sum of the horizontal, let me try that again, horizontal and vertical components of the vectors acting at a point is 0. So what that means is when you look at that point right in here where the two cables and that attachment to the weight come together, then the blue vector, V1, has a vertical and a horizontal component. Part of that vector is going in the horizontal direction to the left. Part of the force of that vector is going vertically. And likewise, with the V2 vector, there's a horizontal and component part. For the weight, there is no horizontal part, it's all going down. So that weight vector, we actually know its components. It's 0 in the horizontal, and because it's going down, it's a negative 20,240 pounds in the vertical direction. So what we're going to say is that this x1, so we're going to look at the components of these vectors, and we see that this angle right in here is 24.3 degrees. But remember, that angle is just a reference angle. The actual angle that we're talking about, that angle that is going to go with that vector V1, is going to have to be 180 minus 24.3 if we're going to get the correct signs to appear. And so that is 155.7 degrees. So, resolving our vector, the x1, the horizontal component of vector v1, is going to be its magnitude, m1, times the cosine of its angle. Its angle is 155.7 degrees. The y1, the vertical component, is going to be its magnitude times the sine of 155.7 degrees. Now, for the green vector, v2, its horizontal component is going to be its magnitude, m2, times the cosine of its angle, and that is, the 44.5 is that angle for vector v2, because that's going from the positive x-axis out to the vector. Its vertical component is going to be m2 times the sine of 44.5 degrees. So when we put this together, what this law is saying is that the horizontal components have to add to be 0 if it's at rest, and this is because we're assuming now this is not swinging around, it's just hanging there, just still. So that's what we mean by at rest. So, and I don't think I labeled, let me change these subscripts. That's x2 and y2. So what we're going to get is that the sum of all of the vertical components is going to be 0. So that's going to be x1 plus x2 plus our, that 0 from the weight vector is going to be 0. So that's telling us that we have m1 cosine of 155.7 degrees plus the x2, which is m2 cosine of 44.5 degrees, and the 0 from the weight vector, that's going to be 0. Similarly, we're going to get that the sum of the y components, so we're going to add the y component from that vector 1 plus vector 2, and then we're going to get that negative 20,240 pounds from our weight vector. The sum of all the y components must be 0 as well. So that is going to lead to, let's see, y1 is m1 sine of 155.7 degrees plus m2 times the sine of 44.5 degrees. And then I'm going to add the 20,240 over to the other side, so it looks like this. Now the claim is what we have now is a system of equations, 2 equations and 2 unknowns. Our unknowns are m1 and m2, and we have very messy numbers that are multiplying those, but we're going to go back to our algebra 2 days there, and so from this equation I'm going to, let's see, let's just solve for m2. So I'm going to say that m2 cosine of 44.5 degrees is going to equal a negative m1 cosine of 155.7 degrees. And then I'm going to divide by that cosine of 45, so I'm going to get m2 is equal to a negative m1 cosine of 155.7 degrees divided by the cosine of 44.5 degrees. Now I'm going to save that for a moment, not for long. I'm going to take that over to this equation right here, my second equation, and now I'm going to substitute this expression in for the m2. So I'm going to leave the m1 sine of 155.7 degrees plus, now I'm going to replace that m2 by a negative m1 cosine of 155.7 degrees over cosine of 44.5 degrees. That's going to multiply the sine of 44.5 degrees, and that whole mess is going to equal 20,240. Crazy. Now, let's simplify a little. Now, this next part you don't have to do, but I like to look, this is all going to go in our calculator eventually, and I like to look at this part right here, which is a sine 44.5 over cosine 44.5, which you may recognize as the tangent of 444.5. So I'm going to replace that just because in a few minutes here, it's going to give me a little bit less to punch into my calculator. So that's a minus now. So we have a minus m1, and then we've got the cosine of 155.7 degrees, and I'm replacing that sine over cosine of 44.5 with a tangent of 44.5 degrees, and that's equal to 20,240. Well, we're making progress here. We look at that left side and we see we have a common factor of m1 that we will factor out, and so that will leave behind the sine of 155.7 minus the cosine of 155.7 tangent of 44.5 degrees equal to 20,240. We're almost there. We're going to divide by all of this stuff. And so we're going to get that M1 is going to be 20,240 all over sine of 155.7 minus the cosine of 155.7 times the tangent of 44.5. Now that's, you got to be careful entering that into your calculator because you're going to need some parentheses in that denominator. If you do that correctly, I believe you will get 15,484.094 pounds of force. That is M1. That is the tension in that vector 1. That's what we found right here. Up in there. That's the tension, how much is coming out this way. Now, once we know the M1, we can take that answer and use all the accuracy in your calculator, and we can now plug it in right here for that M1. And if you do that correctly and don't round and then compute, I believe you will get M2 to be 19,785.832 pounds. That's a pretty cool problem. All right, I'm going to wrap this one up here.